This is the 31st lecture, which I call the Roto-Rooter lecture, and it's going to involve a lot of rotation. Before we do that, I want to show you what I call a telemetric view compared to a Copernican one that you're probably used to. We'll discuss both of them side by side, just for two-particle orbits, and also show some scattering problems that are also not very well known. Or if it's an article again from American Journal of Physics that had some difficulty getting in, but went in finally. The very simple discussion of Newton's F equal derivative of linear momentum with respect to time turning into an auxiliary equation that involves torque and angular momentum. There's a couple of pages in here, and we'll go over that again. That's sort of good sophomore physics course. You should cover that, but we won't hurt to review it. And then I'll show you how to make your boomerang come back, and also we'll make use of our Euler machine to show mechanical analog gyro compass, which is a mechanical analogy for spin. We mentioned that earlier when we were doing other angles, but I didn't show it on the tape, so we'll do it today. Then the tensor analysis of angular momentum and rotational inertia, the quadratic form that we introduced for the superball problem, and then as a way to understand Lagrange versus Hamiltonian, all of that stuff comes back in 3 dimensions now, and you'll see the angular velocity ellipsoid for a Lagrangian approach, and you'll see a angular momentum ellipsoid that would go along with a Hamiltonian approach. Well, this has grown, and we are the originators of something called the rotational energy surface, which is the 3rd way to look at rotors, and I'm going to go over some of the modern stuff, I hope, by the end of this lecture. So let's get started. The basic idea for two particles is that you have a center of mass. This time we really are talking about center of mass and not center of momentum, which we started this course with. So there is, I guess you could call it the center of gravity if you were talking about having these things in a gravitational field, but we don't. We're imagining these things are flying freely now. And the basic idea of having a relative coordinate, r1 minus r2, is key to the standard approach, which this is, to two-particle behavior. The center of momentum, the center of mass this time, is this coordinate right here. And the idea is that you can invert these two equations to get the equations for each of the individual particles that we're used to working with, r1 and r2. Now, let's take a look at this in a slightly different way of doing things. Basically what we're going to do is compare these two. The reduced mass, I would sort of call this a telemetric view, the idea that you're at the center of something and things go around you. That's really what that one is doing. We're attempting to take, say, the hydrogen atom and give it a reduced mass by saying we're going to stand somewhere and watch the other guys move with respect to us. Here, down here, we're going to, instead of having a reduced mass, we'll develop what I call a reduced coupling constant. And that's kind of weird, but it actually is very convenient, particularly for the carrying out the geometrical study of orbits, both oscillator and Coulomb, which we've been doing for the last 2 or 3 lectures. So the basic idea of doing the relative coordinate approach here, relative distance being the scalar magnitude of the relative coordinate of the vector coordinate. Now, in general, we'd be working in 3 dimensions. And applying it to, well, in this case, the Coulomb force, but we're going to compare Coulomb and oscillator forces as we go along here. So the idea is that the sum of the F12 and 21, that's supposed to be 0. That's just a third law, action-reaction cancellation. The conservation of momentum is really what it is. But that allows us to write a single equation involving the reduced mass. And that comes from our solution of those the relative equations. So basically what we're going to do is have R1, the mass times the R1 acceleration minus the mass 2 times the R2 acceleration equal to some kind of force law. In this case, we'll imagine I believe whatever function of R here, and I'm going to divide by the R that's the separation scalar value, and obtain an equation that involves the reduced mass for this. Now, the reduced mass that you use for something like this is the equation that we're actually getting for the relative coordinate. You stand on one mass and watch the other one come and go at a distance r, okay? And you have a reduced mass that affects, and it's called reduced because that's what happens to it. Each one of these masses gets reduced in the approximation that you see here, where I write the mu as a product of the masses divided by the sum. That's the definition of it. And then here I can say, okay, I'm going to divide numerator and denominator by m1, or down here I'll divide numerator and denominator by m2. Either one of those has a series expansion, the first term of which is always a minus sign on it. Now, if m1 is much greater than m2, then it makes sense to do this one. If m2 is much greater than m1, it makes sense to do this one. So those are the two possibilities for approximating the reduced mass, and it is indeed reduced in each case. So that is pretty much what that's involved. Now, as I explained, that's why it's called reduced. Now, the Copernican view, that's this thing down here, is say each particle keeps its original mass, but it feels a coordinate rescaled force field, whatever function of r that you're using for the interaction between the two. Then you take that thing and you rescale it. You do a rescaling of m1 over mu for the number 1, and you do m2 over mu for the number the other guy. So that's the idea of getting the interaction force, 1, 2, written in a sort of a funny kind of way. It'll still have the opposite sign for Newton's third law, but still it's going to be something you recognize. The basic idea is, for example, for a Coulomb force, k over r squared, then this thing is going to be mu squared m1 squared. You have to flip it over because it's in a denominator there. And the Coulomb constant that you used to use, k, will now be replaced for the first particle by k1, which is k mu squared over m1 squared. And for the other particle, you're going to replace it with k2. So they're going to have different, they're going to feel that the interaction is different for each of them, just like these guys say the mass has been changed. And here's the oscillator. If you do it for the oscillator, which is a first order linear force, the Hooke's law, okay, then you replace the Hooke's constant with this. That's a much simpler replacement than this one, since this is inverse quadratic for the force. So that's the basic idea. The idea is really based on what do the orbits look like. Now, TC has the Coulomb one working. I had the oscillator one working in the old program, and then something's afoul with a newer computer that it's sitting on. So I won't be able to show you this one. But this one is, of course, more spectacular. So it's a good thing that that's the one that's working. And if we swing the camera over there, you can see a binary star involved in a very highly eccentric orbit. And I think that's a pretty good example. So the idea, you see, is for the way you can sort of rationalize this is they both have a point, an origin point, where a force is coming from. And the force, of course, is due to the other one. But how would they know that? You see, you could erase one of those particles, orbit and the particle itself, and it would just be a Coulomb orbit around a focal point. And you can do it for either one of them. So that's the whole idea of this Copernican view. You sit on one, you sit on the other, but when you stand back from the thing, that's what you get. And that, of course, is the orbit that you would do in the rest frame, where there's no total momentum of this object, no total momentum or any momentum. So anyway, here's just a list of the things that are true for this weird way, this Copernican, I call it, way of doing mechanics of two particles. The two particles are in synchronous motion. Now the oscillator, they're going to be going around, and I can sort of do it. They're always, opposite each other. So they'll go, always be keeping the center of momentum from moving, you see, and orbit in ellipses that are one inside the other. Here they overlap because the focal point, instead of the center, is where they feel the force coming from. So they're feeling a force from each other, but it's this guy on the other side of this point. This guy says, hey, I've got somebody here that's subtracting me, and doesn't see the other one, but that doesn't make any difference. We then reduce the problem to two orbits that are essentially identical to each other. The periods are identical. The orbits are mass-scaled copies with equal aspect ratios for the A's and B's of the elliptical orbits, and scaled versions of eccentricity, scaled versions of the lambda, the lattice radius, and the orientation is basically opposite, but scaled, whatever the ratio of the masses is. And the orbits differ in size of axes, okay, by that proportion. The orbits differ in placement of the center for Coulomb case, or foci for the oscillator. Okay, the orbital axial dimensions inverse proportion to the mass values. So A1 M1 equals A2 M2 equals the total A that you would associate before with the reduced mass. Use a similar relation for B and for lattice radius. Okay, harmonic oscillator periods, Coulomb orbit periods. Okay, they have proportions in each of them. So that's the thing that is different. Reduced coupling constant yields reduced values. But in this case, they all have to have the same period. And eccentricity must match the value because it's a dimensionless quantity. So that's kind of neat. Three Coulomb orbit energy values set aside the same proportion relations as their axes do. The energy that this one claims he has, and if he doesn't see the other one, It's E1, M1, it's E2, M2 equal, and that's E reduced mass. So this is kind of a weird way to do things, but it's just what we need in order to carry out the program of being able to, with ruler and compass, construct the properties of a two-particle orbit. You basically do it for one with a scaled value that is associated with it, and then the other one can just be copied in proportion with these relations, particularly these relations here. Okay? Now, I'm going to look at scattering, Coulomb scattering. I'm going to look at Rutherford scattering in the situation where the scattering by the alpha particle, the cue ball of the Rutherford experiment, okay, might be of the same, general mass. It's not. It's 4 compared to hundreds, so it's really tiny compared to the gold nucleus. But let's suppose we're doing a Rutherford experiment with liquid helium. So then they'd be equal. You have alpha particles coming in hitting alpha nuclei. Okay? What sort of scattering would you get in a situation like that? Now, I'm going to go ahead here just a little bit and look at that situation. Basically, here's the Rutherford experiment in the lab frame where, in the center of momentum frame where the two are proportionally located. So the beam particle and the target nucleus, okay, the beam particle comes in and it sees looks like a charged object here, you see. So it just scatters off it using our geometry with a little circle, using the energy here, K1 over 2A1 equal E1 relationship, just as we were doing before, except that behind this thing is the other particle coming in and doing a similar thing with a geometry that's rescaled. So I think by looking at this, you see why I wanted to, first of all, get a new contact someday, so that doesn't happen, but why I wanted to have this Copernican view, because the ruler and compass seems to be going forward here. So the idea is, here's the center of, now it's the center of momentum frame as well as a center of gravity frame. This thing is always at the center of gravity if you're in this picture. And basically what's happening is we have these velocities balanced around that, just the right amount, with a big velocity for the little guy and a little velocity for the big guy. So it's a center of momentum as well. And when the scattering occurs, there'll be a scattering angle in the center of momentum, which we'll record on a graph like this that just plots the velocities. And this is plotting the positions, you see. So then, it's really no problem at all to get to the laboratory view. And the laboratory view is that there's this target sitting in the laboratory, stationary, and this particle M1, the attacker, you might say, the thing in the beam, is rushing toward that, and it was standing still, according to the way we think about a lab frame, and it's going to push it off in a direction and give it some final velocity that's different from 0 that it had initially, and then this thing's going to fly off differently now than it did in the center of momentum frame. And the way you find that, using Galilean additions of velocities, is you simply add the velocity of the center of momentum with respect to the laboratory, something that would be constant, to the original center of momentum. So you move your center over to here, and then you get the final velocities that we're going to get by this collision seen in Rutherford's laboratory. Okay? So that's a fairly long-winded description of what it is that I was seeking when I thought up the idea of doing this kind of Copernican view. Now, let's go back to the pool table. We always want to bring up elementary things like boomerangs and playing pool if we're going to do mechanics, because, you know, it brings a human touch to it. If they're the same mass, then these are the same lengths, all of these vectors here that come from the center of momentum. And when I want to go to the lab frame, okay, the frame where the 8 ball was stationary, and I came and hit that at some impact parameter and caused it to do something besides just going forward. If it's I have no English or spin on the ball and it's stationary, you know what happens with our super balls if they're equal mass. This guy comes in, stops, and this guy goes, right? But if you're off center, you see, making some angle, well, what do you get? Okay, this should be a theta here, not a q, which is yeah, that's a little font problem. Anyway, what you do again is you move your center to here. Okay. Now, when you do that by Thales' theorem, you got a right angle, right? So here's Thales' work once again. Okay, no matter how this thing comes out, whatever angular velocity, I'll always have 90 degrees. You see, between the outgoing and incoming. I mean, between the cue ball and the 8 ball. Okay, and you know the game of 8 ball, right? The idea is you want to sink the 8 ball, but not have that thing go down a hole either, right? You want to keep that on the table, but you want to make this go in the hole, right? So you've got to think about, okay, if it goes in the hole, the cue ball is going to hit at 90 degrees, and if there's a pocket waiting over here, you don't want to make that shot. Okay? Just a little common lore associated with Thales, which we've talked so much about. Okay? All right. Well, back to this. And here's where it gets crazy. Because I figured, okay, I've got a geometrical construction for all the details of the center of momentum orbit. Shouldn't I also have a geometrical construction for the trajectories that I see in the laboratory? Okay? No, you shall not, it turns out. The so-called lab frame, if the center of momentum frame is what you're thinking about, the lab frame does not exist. That's what's cool about this. And if you're thinking about the lab frame, the center of momentum frame doesn't exist either. Although it's kind of flying by, but it's going to go to infinity before everything's finished. Let me explain what happened. This is from the article, Geometrical Aspects of Classical Coulomb Scattering, which was the first one I did that sort of went right in. Now, let's just go through what this caption says here. I'm trying to picture what it would look like if I was in a location that was originally stationary with respect to the alpha particle. In other words, Rutherford's experiment was alpha particles standing still. Okay? And beam coming from great distance comes through here. It's not standing still. It's got a huge velocity of some kind. And so the laboratory picture of the center of momentum picture, which is figure 3 that you've already looked at, the scattering begins with both particles infinitely far to the right. That's what I mean by the lab frame doesn't exist. It's at infinity. Okay? Now the heavier particle is at rest then, and the light particle is moving to the left, and we just made it 0.3 miles per day, which isn't very fast, sort of a creep, okay, on this picture, okay, in the scale of the drawing, okay. And this has all happened at infinity, but at some point the heavier particle will appear in this picture, okay. And the way I've got the thing drawn here is that at -1 year before the collision, this heavy particle has shown up. Okay, so talking about 10 to the 7th or 10 to the 8th seconds, we're here. And then we until that is the weirdest phenomenon. I don't know what it is that does that. I'm going to just have to replace all the cables, I guess. But anyway, after say a month or so, you're here, and then after a week or so, you're here. After a day or so, after an hour, after a minute, and you see this is a logarithmic scale of where that heavy particle is that started at rest at infinity. What in the world is going on here?
I have some animations here, Bill, after you get to this point.
Yeah, that is bizarre. Anyway, so when the heavy particle first appears on this picture 1 or 2 years before the collision, it is creeping extremely slowly, obviously, leftward. Meanwhile, the particle is actually going to do the scattering is, you know, way far away, but it's within the neighborhood, okay? And it's slowly pushing on this one, getting it up to speed, you see? And that's the key thing about this. The velocity in the laboratory, which is the integral of the force divided by m2, okay, which, you know, you need this m2 to be fairly light in order to get anything. If it's very heavy, we don't even worry about this stuff. But anyway, this is an integral of the Coulomb, k, there's the m2, and then here's the VCM initial over time squared, you see. And so when you integrate that, you get a V, you see, that involves inverse time, first power, with these coefficients here, okay? And the integral of that is a logarithm, and that's why this is a logarithmic scale. This is the effect of having an infinite range of your potential, which is what a Coulomb does. The integral of this thing is going to be logarithm. Okay? So essentially the whole idea of a perfectly perfect lab system is bogus. You have to have this ridiculous situation where everything is infinite apart, then finally comes in with great distances and long times, you see, and then the way this is scaled, you see, when this guy here is creeping slowly leftward, while the lighter particle is still over 100 miles off to the right, so it's getting a year to get here. Then the heavy particle continues creeping until finally the lighter particle arrives in this picture right here at about 5 seconds before the collision, okay, and moves through in about 12 seconds, okay. Most of the momentum is transferred in 3 or 4 seconds. Okay, and then they're off to the races, okay, with their respective races. This one now has some speed comparable to this one. Isn't that weird? So you're not going to do a ruler and compass construction of these trajectories. You're only going to approximate. Okay? Now you figure, okay, well that's fine, but maybe I could show where the asymptotes are, you see, in the lab frame, okay? Because I know the angles they have. I should be able to locate them. No, sorry. That's what they look like. As the years go on, the asymptotes keep moving. This shows you how people like Goldstein and all those are writing books, they didn't really think about it. Okay? Logarithmic recession of tangent demonstrates non-existence of asymptotes for pure Coulomb scattering in the lab system. Lab system is just really terrible. It's not existent in the ordinary sense that you might expect. We have short-range force, fine, it all works great there. But this is not a short-range force. It's got a logarithm. At t equal 10 to the 3, the slopes of the tangents are shy of the values that they're going to have that we worked out with our geometry by only 1/100 of a degree. or twice that, respectively, talking about 2-to-1 mass ratio here. Okay? But that doesn't matter, you see. They're getting better and better at being the right angles as they creep over the years. 10 to the 7 seconds here, a year. And then, say, 5 years. And then, you know, a century, a millennium, you know. The life of the universe, right? It's about here, right? It just keeps creeping, you see. This is assuming these are the only 2 particles in the whole universe. Because obviously they're going to go very far and run into things, but in the real world. But I thought you should see this. This is what I guess Abraham PHYS means by the devil is in the details. This is very devilish, but it's what Coulomb does. If you take it literally, and we have to when we do our things. It's true for the attractive one as well. If you do an attractive one, the fixed particle gets sucked in from infinity, and then the scattering occurs, and then they go out and they have the same asymptote problem in reverse. So, it's just before Christmas, and I didn't want to make you depressed, but you should be aware that one of our simplest classical potentials has got this defect. Defect, it's the way it is. It's not a defect, it's what it does. All right, let's get back to something that's much simpler, and that is adding to the Newton linear equations something that's needed to discuss the rotation of objects, particularly rigid bodies that we have not said much about it in the course so far. Really, the whole Unit 6 is devoted to rigid and semi-rigid. I'll show you a little bit of that. It's one of the more voluminous chapters in the text, so we're not going to be able to cover all the details, but I'm going to give you the interesting ones, I think, right here. So, what we've got here is the idea that linear momentum times its lever arm in a funny kind of way that involves the sine of the angle between them. That's what you get when you have the cross product of R and P for each of any number of particles. We'll imagine 3 now. 3 particles are enough to reproduce all of the dynamical theory that you would have for a rigid body. So as soon as I get 3 particles in some kind of arrangement, either like a symmetric arrangement, asymmetric arrangement like this, and I had one here that is a more symmetric. If I use 4 particles, I've got this thing. If I want to use, I'm sorry, that's 5. 4 on the outside. If I want to use 4 and make a thing like that, that's a example of something that is fairly simple, but it's got one more than what we're going to need. Just 3 particles like ozone molecule, it's not terribly stable. None of those molecules with 3s are really stable, but they make nice radicals, which spectroscopists are now able to study. In any case, total angular momentum here, sum over all the particles of R cross P, that's R cross R dot with a mass attached, is our total angular momentum, which is what we're going to work with. So think of 3 bodies. It's the next thing up from 2. We do have a center of mass, center of gravity, if you will. Again, it's a weighted average of the coordinates of each of them. Okay, so the idea is to take the derivative of the momentum, total momentum, and it's going to give us a Newton equation for rotation, for the rotor momentum summed in terms of, and that's what's going to come out here, is in terms of what's called a torque. And the torque is simply a radius cross the force for each particle. For each of the 3 particles here, 1, 2, and 3, R cross F is being summed up. Okay? Now, what we're going to imagine is that this F total can be broken up into an applied force plus constraint forces. You see, that's the old bugbear of classical mechanics, is there are more forces than what meets the R, or what you apply. So internal constraint that the coupling force would give, it appears to be a major nuisance when you have all of these things that you have to worry, and this is going to go up quadratically as we have more and more particles. So it's fortunate we can ignore those, at least in the simplest approximation. And you can see pretty clearly that if Newton's third law applied for the two, it also applies for these. And so you have, for every 2 with a minus sign, you have a 2 with a plus sign, and then you have the forces that are constraining them. 2, 3 is equal to minus 1, 2, and so you can arrange to have those things cancel. These two forces can be ignored completely, and we're just left with this guy, the applied, what you're putting from the outside. So these are the what we call, I would call, the rotational Newton's equation, even though it was a long time before anyone actually wrote an equation in this form. Recall that the cross product and all of that kind of stuff is Josiah Willard Gibbs' abstraction of the quaternion stuff. And this notation now, it is not used by Maxwell, but we use it for all sorts of things that involve curly behavior, and angular momentum is certainly one of them. So this equation right here is replacing, or not replacing, but is in addition to this one. And you need both of them to really do any work at all. That I think becomes clear when we did the situation of the trebuchet, or the lever, flying lever. If you impulse a lever and then have it go and make all of the different cycloids that each one of the parts of the lever do. You saw that we really needed 2 equations, one for the linear and then one for the angular momentum. So these taken together in 3 dimensions are 6 equations to describe anything that's rigid, you see. Constraint forces have to be strong in order for this to really work clearly. The remaining, if you have n particles, the remaining 3 minus 6 equations consist of what we call vibrational modes, normal modes, or if it's a complicated thing, we have some kind of generalized coordinates describing them. And of course, this is a field that people keep adding to. What sort of generalized curvilinear coordinates can you think of to describe the behavior of molecules and nuclei, atoms, and all sorts of 3-body problems, 4-body, well, you know how many bodies there are in the modern atomic and molecular, and now that we're looking at the nucleus and subnucleus, there seems to be an infinite number of bodies that we have to worry about. Fortunately, they're waves, so maybe there's a way around this conundrum, but it doesn't look all that encouraging. However, this sort of thing was encouraging at the very start, so we get to have these 2 equations. Now, I want to show applications of this, a couple of them. And let's go ahead and get one of my props here, which is the boomerang, as a example. Please don't block on me. The idea is that you take this boomerang and you throw, and you usually throw it at an angle so that it's not like this. If you throw it like that, it's very likely just to dig into the ground. But if you just give it a, sort of a natural angle to it, it will begin spinning, okay? Now you have to imagine what's happening as it's spinning. the sound that a boomerang makes that is in the famous song, My Boomerang Won't Come Back, which I've tried to find on YouTube and I haven't been able to, but if you do locate it, please tell me, because we're going to put it in the next video we do of this. But anyway, a boomerang goes, right? And then, which is what helicopters do. If you know, Vietnam helicopter, what's going on there, right? What's going on there is that the upper wing, okay, upper blade, okay, with the translational motion that you've given it, is adding its rotational velocity to its, you know, the airflow of velocity over the wing, or the blade, okay? So it's, and this one down here may actually have no wind at all if it was just right, so that the velocity from the rotation canceled the translational velocity going forward. So you just hear the top wing go, okay? So that's the of the boomerang mix, and if you throw this thing, it does make that sound. So do all the plastic models and wooden models that you can buy. This is the only aluminum one I've ever seen. It's the one I made. We made several of these. I made one that was about this big. It was really spectacular. But anyway, when you throw this thing, the means there's a lot of lift on this side and very little lift on this side. So you have a high aerodynamic lift on the up side and much less on the lower side. Okay, and that's an unbalanced lift that gives you, and use your right hand, a torque. Okay, so this is the way to think about torque. It's just to put your hand in a curly right hand fashion, right hand rule, and your thumb will be the end coming out of this plane of the screen here. The end is supposed to be sticking out. Okay, is that clear? And since dl dt, the rate of change of L, is going to be equal to n, and n is perpendicular to L, it's not going to increase the value of L in magnitude, but it is going to change the angle, and that's what causes the boomerang to orbit. Okay, so this plane is going to orbit till it's facing, and then it's going to come around here. And if this were perfect on all the forces there were, it would just simply come back. You know, if there were no friction and you were in some liquid helium bath or something like this thing could orbit forever. Okay? That's not what happens. What happens is that there's another torque. And that torque is the torque that this blade here feels as it comes up into the air that has already been given momentum that way from the blade that was just there. This is what I call bad air. The bad air is a sailor's terminology. When you get in the air that has been momentum changed by your competitor in another boat, okay, it screws you up, and so you try to avoid the bad air. Well, this can't avoid the bad air of its previous partner that gave momentum that way. So what you're getting is an unbalance this way, okay? You're getting a torque this way. Okay, let's see if I've got that right. I'm over here, and I'm feeling his bad air pushing me this way, okay? So that's a torque this way, a little one, okay? An additional lifting torque that's got to be attached up in the screen here, which will bring the angular momentum up gradually, okay? Now in a well-designed boomerang, which is what we were trying to make, well, the idea is it would be just enough so that by the time it got around the orbit, it was level. And it would slow down too because of a lot of drag, right? So the idea is that I can throw this thing and it can go a great distance and then come back and stop and hover down. And we, you know, if that works, you're safe because you don't want this thing coming back like that, you know, like this, right? And sometimes it does that, so you know we sometimes have to run like hell because this thing is lethal. All right, but you know, play with these things. They do it really nicely. They actually continue to roll over, so the boomerang can come back. If you have a three-bladed boomerang, it's immediately going to loop. and then go the other way. And then loop back, you see. So 3 blades are really uncontrollable. 2 blades, you can get it to do this. I thought you'd be interested in seeing that. You know, there's a lot to be done with improving on what the Aborigines used to actually get their food. They would throw these at birds. And then throw them at kangaroos. It just make kangaroo maddening. But you can get small animals with these things, okay? And anyway, all right, now, we've got a little bit of time here. I want to show you a couple of things that are kind of neat. And I'm going to rush through the mathematics on this because we've kind of done a lot of it already. Basically, bam, there it all is. What we've got here is a velocity is equal to angular velocity cross r, okay? So r dot, omega cross r, is being stuck in here for r dot. Okay, so I get a triple product, triple cross product, okay? Levi-Civita analysis breaks that down into a dot term and then a thing that, well, we're working it out here, r dot omega, and then r dot omega times the vector r. So I get the omega clear of that, and I get a quadratic expression here involving the unit operator and then a tensor. That's just an outer product of 2 vectors, okay? And that looks like this in a matrix. I have here all these cross terms for x, y, and z. It's 3-dimensional now. So basically what we're doing is we're making an inertia operator or tensor or matrix that describes the connection between angular velocity and angular momentum. So it's this old thing about getting velocity to transform into momentum by using a matrix, which was our big thing we did in chapter 11 and 12. Okay? Now, just to give you an example, just to feel what this is telling you, let's imagine that you've got a mass that's off-center. Okay? It's located with an r that's at square root of 2, square root of 2 is 0, 45 degrees with respect to the bearing axis, and you're going to spin that thing. Well, that means you better really hold on hard with this bearing because this is, you know, going to, okay, vibrate like crazy if this is rotating fast, okay? And what's going on is there is an angular momentum associated with this motion. We have an omega here of whatever, and it's all in the y direction, and x and 0 at the is going to be 0. This thing is located over here at x equal and y equal the same. Okay, it's got two coordinates right at this moment, but that's going to change, you see, as time goes on. But let's just look at what is the torque, and the torque is going to be the rate of change of this angular momentum, which is going to be flopping around according to, and this is where you use the matrix to figure out what this omega, this thing right here, turns into after you apply this matrix as angular momentum. And if you do that, you get an angular momentum that is at minus the square root of 2 and at square root of 2. So it's just the opposite 45 degrees to this one. But it's going to be attached to this body. So this angular momentum is going to be doing this. And the rate of change of that angular momentum, if we're going this way, is this way. So you're going to feel a torque right at this moment. If this is the rate of change of the angular momentum is up, okay, that's a torque in this direction. So you're going to feel this thing jerking you this way at this moment. And then as it comes up here, it's going to be jerking you this way and so on. That jerking is going to be rolling with this thing as it rotates. So I'm just trying to get you used to doing this to make a torque, and then that's the thing you're going to feel when you hold that bearing. Okay, so you better have that thing down pretty tight. It's going to try to break loose. All right. Now, we can go ahead and we can figure out energy for this thing. That is 1/2 mv squared. That's omega cross r dot omega cross r. Again, a Levi-Civita combination, this time giving us a bunch of scalar products. Okay? But that scalar product can have the omegas pulled out of it and give me, well, the same old inertia tensor that we just worked out. Okay, this is the Dirac notation for it right here. So here we have the quadratic form that describes the kinetic energy of any rigid body for which you can give me a sum of masses times the various coordinates of the masses. So I have to sum over three things if I had a three-body guy here. All right? Or I have to integrate if it's a continuous thing. So those are all things that we're going to skip over. We're just going to assume that we've got some numbers here, and then we're going to assume by symmetry that if we pick the right axis for some of the things we're going to look at, that it boils down to this. Now this is a symmetric matrix, so you know this exists, no matter how bizarre a shape something might be. Some Henry Moore piece of sculpture that you've got that's just, you know, amorphous shape. There's no symmetry at all. But inside that amorphous shape sits somewhere a perfect set of orthogonal coordinates that are the principal axes of that inertial body. And when you get there, you'll have a principal inertia that are that. So there is a frame in which this becomes simple, and your kinetic energy is just a quadratic form of the simplest kind. No off diagonals. The ellipse that it describes, ellipsoid I should say, that it describes will be, you know, as though that thing was really made to be an ellipsoid. You cannot distinguish inertially the easy thing from the hard thing. But anyway, the kinetic energy in terms of momentum, and that's an interesting thing which we've already done. All you have to do is take your kinetic energy with the omegas and stick in there omega equal inertia tensor minus 1, the inverse of that matrix, times L. So if you do that, okay, put that in there, first of all put in L for I dot omega, okay, and then omega itself is L inverse is I inverse times L. That's what you're going to get. You're going to get a quadratic form involving the inverse of the inertia tensor, which if you're in the right frame is simply 1 over the principal inertia values. So there's the expression in Hamiltonian form now. This is Lagrangian form, right? So this is going back to chapter 12, which we did for just superballs. We did that kind of thing with a two-dimensional velocity space and momentum space and a Strangian space. There's also a spherical, a Strangian that's in between these, but we're not going to make use of that right now. We've got something else we need to try called the rotational energy surface. But in any case, imagine an ellipsoid with another one sticking through it. These two have this wonderful duality that a tangent plane from this one is normal to the direction of the omega, okay? And the omega was sitting on a tangent plane that is perpendicular to the L. You've seen this before, right? This is your Hamiltonian Lagrangian mishmash, okay? And there's an omega dot L, there's a Poincare relationship with this. We won't do too much with that right here. That's something that's in the text for other uses, okay? So, what you make use of here, however, is that omega is generally not conserved unless it is aligned to the L, or the body has symmetry. So omega is usually out there if this body is flying without any applied forces at all, just falling, you might say, then these things are true. Now, omega dot L is 2 times the kinetic. That's a result that we saw with quadratic form. So that's a constant of motion as well, even as this thing rise. But omega is not conserved. Okay. Now, what we need to do is go ahead and look at the formal parts of this. Here's the canonical momentum we defined. Okay. And the Lagrangian here is kinetic energy, so we don't worry about any outside forces with this venture. So L is the omega gradient of the kinetic energy. Okay? Say partial derivative with respect to vector omega of this. That's just I dot omega. Okay, so there's L equal I dot omega written out in the as though it were the first equation of Lagrange. All right? Then I can take the Hamiltonian, which is this guy right here, and differentiate that with respect to L. Okay, the gradient with respect to L. Okay, that's better be omega. Okay, and it is. Okay, so that's the inverse right there. All right, so you have Lagrange's first equation, Hamilton's first equation. It's just the geometry of ellipsoids. Pretty cool, right? Easy to remember. All right, pretty simple. Okay, and for a general asymmetric body, say a block, a brick, okay, there will be an L ellipsoid and an omega ellipsoid, and there'll also be an L equal constant sphere, okay, and that's what you would probably want to work with. Now what's really funny is the French took this over. French are the Lagrangian, okay, so all of their rigid body stuff just worked with velocity, which wasn't constant, so it was a pain in the ass. It's only in the Russian mechanics books that I find that Landau says, hey, that's ridiculous. Why do those frauds do that? Let's do it right. Let's work in angular momentum because it's constant. Okay? Well, it's constant in the laboratory. It's not constant in the body. Okay? But its magnitude is constant. These for non-relativistic problems. Okay? So it has to be on a sphere. L magnitude is constant. The vector is constant in laboratory, so the magnitude, which would be the same for everybody, classically without relativity, that would make it so all I have to do is intersect a sphere with the angular momentum ellipsoid. Forget that omega ellipsoid. Forget that guy. Just work with this one. Okay? Pay attention to Hamilton. Okay? So once you do that, you get these topography lines for the vector L. And that's what's going to, we're going to show the results of that. Okay? So in a body frame, L moves along the intersection of the L ellipsoid. You see, in the body frame, the body's going all over the place. The L is fixed to the stars, so this L is going to be cutting through the body's ellipsoid and making trajectories, which we will solve by geometry. That's kind of neat. Okay? Now there's another way, two ways to look at it. This is our addition to the pile of physics. Okay? This is what Landau is using in his book, and all the other books use the omega, which I won't mention anymore because it isn't as useful. These two work for you. Now this one, you see, is a constant energy surface. All I do is take the kinetic energy, which is the total energy now, and say it's a constant. And if I do that, then I get a ellipsoid. Well, if I don't have any minus signs down here, I get an ellipsoid, okay? Like that, okay? That's the plot of the ellipsoid. Energy equal constant with a range of J values all over it, okay? Jx, Jy, Jz can be whatever, but they have to be on the surface, you see. Okay? Here's what we decided to do. That one right there has a whole bunch of J's for a single energy. If you're going to do spectroscopy, you're going to get a whole bunch of energies for a single J. So this makes more sense. What we're going to do is we're going to plot E radially with J equal to a constant. It's a quantum value. It's conserved quantum value. So we're going to have this be a constant, and then we're just going to plot this multipole function, quadratic multipole function, which looks like a bar of soap with a punch in it. Okay? That's the rotational energy surface. You see, J is a constant for that whole surface. E is a constant for this whole surface. You overlap them, you see where E and J play with each other. Okay? Not much sense to do that, but I just wanted you to see that they are sort of opposites of each other. But this one does show the separatrix very nicely. the separatrix between two kinds of motion, here and here. It's like the pendulum, where you have a saddle point, a separatrix, and then other kinds of motion outside that very different from what's inside. Okay? Except that when you look from the top, this is the inside and that's the outside. So you've got two kinds of pendulum on one three-dimensional space for an object that would have different inertias in three principal directions. Okay? Now, this can depend on the inertias. If you have the inertias very nearly equal, or two inertias that are very unequal, you have a degenerate case. This is called an oblate. This would be like a frisbee. It's nearly oblate. Still a little bit of funny business there. And this one is nearly prolate, like a bowling pin. Still a little bit of funny business. It's not quite there yet, but just to show you how these behave, what's really cool is that these rotational energy surfaces are a way to geometrically define the eigenvalues of angular momentum problems. This is a J equal 10 water molecule. Okay? Well, no, it's actually a J equal 10 ozone molecule, or something that's got, I shouldn't have spoken. It's just more like a fluorinated methane. Okay? That's what it is. It's a prolate top. It's got more inertia around here than it does going, flipping, than it does around there. Okay, so the inertia is always the same for any axis here, and then it's the inertia is much less up there. Remember, the Hamiltonian has 1 over the inertia as its value. So that's what we're looking at here. And then you just take angular momentum cones from quantum mechanics that have to have the total angular momentum, J times J plus 1, be a constant. Okay? And J times J plus 1 is bigger than J equal K. K equal now J minus 1, J minus 2. Okay? So you get a little bit of an angle here, and that's the angle where you find the energy for the very maximal value of the, this is what we call a Z component in quantum mechanics, axial component, okay? So you just find all of these angles and see where they hit, and you get a trajectory on there. And here's what happens if you have a water molecule. Now what I'd like to show you is what goes on with these trajectories, because these are trajectories that are followed by J if you could ride in the body frame. So let's, since I've cleaned up the air bearing here, let's go ahead and plug it in and get it going. And what you'll see here, if you zero the camera in here, is a pool ball that has 2 brass rods in it. Ignore the different color in the middle. That is the same density of plastic as the rest of it. Just has some dye in it, so it's a clever way to put the number. And then I drilled it out on a lathe so that it had a big brass rod, which is pointing at the camera right now. I'll turn it perpendicular, and you can see it's thicker than the little brass rod in the middle. Now, if I spin around the big brass rod, okay, like this, that would probably be the highest number. You see it persists a little bit because I didn't get quite on there, but it just hangs in there. It doesn't do anything too much. Simple, little funny sort of motion, which is predicted by that surface, but it's a little harder to see than what I'm about to show you. And then another way to swing this is this way, where I swing all the metal together, and that one also stable. If I can get it on there, I could make that one really perfect. I'll just try to do it. Well, that's not really showing it. It's really, you really have to get these guys on the axis for you. Anyway, this is the low energy state. This would correspond. That's not too bad right there. That corresponds to rotating around on one of these trajectories. And I never can get it quite in the center. I'm always, a little off. But that's the angular momentum, which remember is fixed to the stars, going around in the body. And the body is grinding around with something that's fixed to the stars. Okay? And then the other one I was showing you was when I was at high energy, and it ground around on one of these trajectories. But the interesting one is right here. And that is, I've even drilled a little hole there so I can stick a ballpoint pen into it and use it as a bearing. I'll just start this thing rotating, okay? I'll just start it at an arbitrary angle. There it is. Now I'm holding it. So you'd think it would it stay there for me? Yes, it would, maybe, for a second or two. And then turns completely over. And then comes back. And then turns completely over. And then comes back. And it's not regular because it is really sensitive to any sort of perturbation or burbling going on with the air that's supporting it. If I was in the space lab, I could do this and get it to reproduce very perfectly and stay exactly on, and let's take a look at this diagram again. What I did was I put this thing on a point somewhere near the saddle point. If I got it right on the saddle point, in principle it could stay there forever. But it isn't any more probable it's going to do that than if I were to try to balance this pen exactly on the thing. It's going to fall at some point. I'm going to be a little off, and it's going to exponentially leave that point. First it doesn't leave, but then all of a sudden, boom, it goes on one of these curves and sits over, and comes and sits for a while over here. And then, boom, it's going to come back, presumably on a different point, and it may get perturbed on the way and end up over here, in which case it's going to go that way instead of this way. So all of these are all flow lines for angular momentum vectors, and this is the bizarre place where it can't make up its mind which way it wants to go. And so it behaves somewhat bizarre. And you can see it now, it's even turned a little bit. But you can see it slowed down there. There it is, very nicely rotating, and then all of a sudden, it speeds over. It's upside down now. Now what I need to do is make it double colored so you can really see that it's red and green on top. So this is a really beautiful example, I think, of the behavior of the rigid top. Now, a water molecule, like this one, for example, or this one, okay, a lot of molecules that are bent like this, CO2 is not one of these, but when it gets excited, it's like one of these. What I try to do is I try to rotate the thing this way. This is the unstable axis right here. Rotating around that axis is not a problem. No matter how clumsily I throw it, I usually get a pretty good stable rotation. Throwing it like a boomerang, that's also stable. That's actually the lowest energy state, okay? And this is the one that's weird, okay? So as I try to spin that up, I don't know if you can see it, but it's going back and forth. If I try to keep it pointing to my left, it's very quickly over this side and then it's back again. That was a terrible throw. There you saw a little bit. This one is a little easier to see because the black thing shows up fairly easily, okay? But do this with any rigid body. Tennis racket. Try to make a tennis racket go like that without twisting. The probability that you get it to do a full rotation without twisting is very low. And you can bet people that they can't do it, and you'll mostly win. Now here is going from symmetric prolate to symmetric oblate, and here's what the quantum spectra does. That's really cool. You can see the aperitrix region where the levels are doing avoided crossings, or not crossings, they're doing voided separation. That is very neat. Now I'm going to just end right here with this. This is the upshot of using rotational energy surface for spherical things. This is the energy levels that come from that, and the spectra that comes from that is right there. There's a whole bunch of it on the wall over there, where you see that each of the angular momentum cones sitting in the rotational energy surface can be directly related to a spectral line. These are actual beats between ground state and excited vibrational state. So I hold this up as a really successful use of geometry in thinking differently about things that rotate. And these are deformable spherical tops. So the deformation of the thing as it rotates is represented by how far from the value you are on a molecule like this. If I try to rotate this thing around that axis, you see the centrifugal force would stretch these a little bit, but not much. They're much more likely to bend, and that's what's going on when I rotate it around that axis right there. Then the centrifugal force can flatten the molecule a lot. So the energy goes back down. Remember, when the inertia goes up, the energy goes down. So this phase space energy surface is discussed somewhat in Chapter 6, but there's a lot of other stuff that you might want to look at if you're interested in following that up. In any case, that is pretty much it. I'm going to mention that the rest of the book has discussions of the precession of symmetric oblate and prolate tops. This is an oblate top, then the prolate here, and then an oblate, spherical in various different ways of changing the parameters to make something happen. So here we go with an oblate ellipsoid and a prolate ellipsoid, and the geometry of it that makes the thing move. So you can see anytime you throw a prolate top into the air, most of the time you won't get a throw like that. Most of the time you'll get something like that, where it lazily precesses. That's what we're talking about here, as precessional motion of the object. Now, while we're on that, I should show something that I missed completely. Let's bring the camera over here to the Euler angle machine and make it dance. I'm going to take the operator away. And what I'm going to do is I'm going to start this thing up with an angular momentum this way. Okay? So I'm going to get an angular momentum that's up like this. And then if I apply a torque to that thing, it should respond accordingly. If I apply a torque this way, okay, that is, turn it this way, there's the torque with my thumb, right? And then there's the angular momentum with my thumb going this way, because I turned it this way, right? Okay, and then I apply a torque this way, it should bring it to the, let's say, the north, okay? Let's just call this the north star, okay? Now, if I go the other way, okay, if I apply the torque down, okay, make this thing go around this way, the torque is this way, I'm still going to have the angular momentum on the North Star this way, okay? So let's do that. Goes down, right? Now, here's an easy way to see which way it goes. And this is really what's going on. This is relativity, okay? The idea is that if I have it going this way, and then I go this way, well, it's fine with that, because the relative velocity between it and the thing it's connected to is less. It wants to keep the beats down, and the beats are the difference in angular velocities, okay? Whereas if it's going this way, and I go this way, it wants to turn over to point in the direction of the angular momentum that I just gave it. I'm using my right hand. I gave it that kind of torque, and it wants to get with that, so it'll turn over. Now this is analogous. You see, the thing we did with the spin in the oscillator, we had the spin model. What we're doing is we're saying, okay,
what does spin do when you apply a C-type vector to it, namely this operator right here, and it will precess around that thing. So basically, if you have a magnetic moment, right-handed, okay, magnetic moment like that, then and a magnetic field this way, it's going to line up with that magnetic field and actually oscillate around it. Okay, that's that little oscillation, that precessional motion is the. If you turn the magnetic field the other way, okay, when you've rotated it with a spin north, if you put the magnetic field south, let's get this thing really going here, and put it south, it points that way. Now that's exactly what a gyroscope mounted on a very fine bearing does in a gyro compass. The gyroscope is trying to get this relative velocity with the Earth's motion to be low as possible. But you can also do it by L equal dl dt equal to the torque, and you can analyze what the gyro compass does. But it's a lot easier to say it's trying to get get the relative motion the same or low. And that was really what's going on with the spin, the two-level quantum system. Okay? And it's funny, the two-level quantum system is simplest mechanics. When you do it with the waves, it's the easiest one. All of the other stuff is more difficult. That's relativity, right? The actual linear relativity is more difficult than this stuff. Okay, well, that ends the course. I think we've gone full circle here now. We've come from the ellipsoids of superballs to the more well-known ellipsoids of the angular momentum. So I hope you enjoyed it.
Yeah.